All right, we'll go ahead and get started. Welcome, everyone, and thank you so much for being here for today's expert briefing on AI tools for addressing conservation and biodiversity. My name is Jason John. I'm the Deputy Director of the California Council on Science and Technology. I'd like to open our briefing today by acknowledging that we are calling in from different locations in what we now call the state of California, which is home to many indigenous communities that have stewarded this land since time immemorial. For those of you who don't know us, the California Council on Science and Technology, or CCST, is a nonpartisan, nonprofit organization established 35 years ago at the request of the legislature. CCST was created to provide science and technology advice from the wealth of outstanding academic and research institutions in our state directly to policymakers. California is lucky to have such an incredible network of expertise, and our job at CCST is to help amplify and translate the expertise in this network into actionable advice for policymakers. We do this through a number of different mechanisms, including briefings like the one you're attending today. We host workshops, write peer-reviewed reports, and run the CCST Science and Technology Policy Fellowship, where we place PhD scientists and engineers in the executive branch and the legislature for a year of government service and leadership training. If anyone watching is interested, or if you know someone who might be interested, applications for next year's cohort are open through next Monday, March 10th. We're happy to connect if you have any questions. As part of our mission, CCST is advancing work related to our disaster resilience initiative to help the state better prepare for and respond to ongoing, complex, and intersecting disasters that affect public health, our economy, and our environment. These include climate change, extreme heat, power outages, and the COVID-19 pandemic, which have and are still radically disrupting the ways in which Californians live and work. These disruptions can often be destructive and painful, and they can show us where there are needs or opportunities to redesign our systems to be more resilient and sustainable. Through our disaster resilience initiative, we seek to deliver science and technology advice to reduce harm and improve the lives of all Californians now and looking into the future. This briefing is the latest in a series of conversations about the intersection of AI and society. I hope you'll stay tuned for several upcoming CCST expert briefings on AI on the grid throughout this year. Today, we're focusing on AI tools that can help address the biodiversity crisis and assist the state in realizing its conservation goals. Biodiversity is declining globally at unprecedented rates due to a variety of cascading and compounding anthropogenic impacts, including climate change, habitat destruction, pollution, and overexploitation. Governments around the world, including California's, are committing to aggressive conservation goals to address this crisis, but often face challenges in obtaining the high-quality data that are required to inform management and conservation decisions. Advances in the fields of artificial intelligence and machine learning are a promising avenue for supporting researchers and practitioners in the conservation space. As the capabilities and accessibility of AI continues to grow, bringing with it both positive and negative disruptions to our environment, workforce, and economy, it is critical to have these discussions about how AI can safely and ethically be deployed to benefit all of society. I'd now like to introduce our moderator, Nathaniel Roth. Nate is the Department of Conservation's Chief Science and Data Advisor. Previously, he has served several roles within the Department of Conservation, most recently as Geographic Information Officer and Geographic Information Systems Coordinator, overseeing the department's geographic data publication practices and the information technology infrastructure that support them. He was the liaison for GIS data between the Department of Conservation and other state, federal, and local agencies, as well as private non-governmental organizations. Nate has also served on the staff of the Information Center for the Environment with the Department of Environmental Science and Policy at the University of California, Davis. During his 15 years at UC Davis, he worked on a variety of projects, including geographic data development, complex spatial numeric modeling, data publication and cataloging, and outreach related to project work. We're very lucky to have him here with us today, and welcome, Nate.
Thank you, Jason. It's an absolute pleasure to be here today, and I'm really excited for today's conversations. California's ecosystems are facing increasing threats from climate change, habitat destruction, and biodiversity loss, placing immense pressure on the policymakers and researchers to develop innovative solutions to these threats. To address this crisis, governments around the world, including California, have committed to the 30 by 30 initiative with the goal of conserving 30% of the world's lands and waters by 2030 to protect and restore biodiversity. Artificial intelligence is emerging as a powerful tool in addressing these challenges, offering new ways to monitor species, predict environmental changes, and enhance conservation strategies. Indeed, AI is already here. It's an essential part of biodiversity conservation now, not necessarily as the fancy modeling or complex predictive tools, though those exist that we frequently think of. AI is assembling many of the foundational data sets. It's counting fish, identifying species in trail cameras, and parsing eDNA as we speak. Our panelists today will provide essential context on how AI is being applied in biodiversity conservation and explore expected trends in the field. Our discussion will highlight how these advancements are shaping conservation efforts within California and beyond. I'm going to now introduce each of our panelists to invite each of our panelists to introduce themselves and tell us a little bit about their work. First for us is Sara Beery, assistant professor at MIT.
Hello, thank you so much for having me. So I at MIT fundamentally work on the development of novel machine learning methods that are really driven by the challenges we see in applications in biodiversity and conservation. And in that space, I work with many different modalities of data. So everything from satellite imagery to camera traps, like you mentioned, very large scale citizen science data. Maybe if any of you have ever taken part or participated in iNaturalist or eBird, as well as things like collars for animals, or bioacoustic sensors, and the list goes on. And I'm actually very fascinated in this question of how we can actually start better sharing information across all of those different modalities that are giving us complementary but somewhat unique perspectives on the world, and how AI can actually play a role on helping us elucidate some of those complex relationships between ecosystems, within species, and across species.
Thank you, Sara. Next, Kumar Mainali, senior data scientist with the Chesapeake Conservancy.
Hello, everybody. My name is Kumar Mainali. I'm a senior data scientist at Chesapeake Conservancy and also visiting faculty at University of Maryland College Park, where I teach data science and machine learning courses. My work is related to biodiversity conservation, climate change, and environment. At Chesapeake Conservancy, we develop very high-resolution data products that are applicable for conservation, decision-making, and management. And I specifically work on land cover type of problems and biodiversity. I apply a range of tools, including mathematical tools to classical statistics and machine learning and AI in biodiversity research. In biodiversity, we have applied traditional machine learning as well as the artificial intelligence, which is deep learning based models for making predictions. And a strength of these algorithms is you can make a prediction with very high precision and accuracy. And I am also very fascinated by the power and application of AI, and I also strongly advocate for the democratization of AI tools and data. Thank you.
Thank you. Next, we have Bistra Dilkina, co-director of the Center for AI and Society at the University of Southern California.
Thank you, Nate. Hi, everybody. I'm Bistra Dilkina. I'm an associate professor of computer science at the University of Southern California, and I also co-direct the UC Center for AI and Society. I'm really happy to be here today to share some of my work and perspectives on AI for biodiversity. So I actually work mostly on building AI approaches for more effective decision-making, planning, and resource allocation. So more on the decision-making side as opposed to the prediction side, especially in context with complex constraints, objectives, and limited resources that must be allocated as effectively as possible. So in my work in AI for biodiversity conservation, for example, I have looked at different planning and decision challenges, like deciding where we should protect wildlife corridors in order to alleviate the negative impacts of habitat fragmentation due to human development, or, for example, predicting biodiversity shifts, taking into account projections of changing climatic conditions, but also the species' dispersal ability to move in space over these decadal timelines. And then thinking about how these kind of projections with both climate and dispersal can actually impact our conservation decisions of what we think we should protect today, but taking into account the biodiversity of tomorrow. So all of these problems are, characterized by the fact that we want to make as effective decisions, but we have many, many choices. For example, US is huge, right? And so there's many options, while at the same time we have limited resources of how much resources we can invest. And there's other problems that touch on that same space. For example, a related problem that also has a connection to biodiversity is planning where to do prescribed fire burns in order to minimize wildfire risk. And in that work, for example, again, it's a planning problem with limited resources, but we can incorporate habitat considerations and biodiversity impacts in addition to, for example, protecting watersheds and human infrastructure. And finally, one other aspect in which AI can play a role in biodiversity is looking at illegal wildlife poaching and trafficking, which is a global problem that is the second most important threat to biodiversity in the world, second to habitat loss. And so there we have leveraged, for example, AI to predict hotspots of poaching in protected areas, to allocate and plan for park ranger patrols, and to predict and understand illegal wildlife trafficking on the global flight network. And then again, think about driving factors and how to allocate limited interdiction resources. So there's really many, many ways in which AI can contribute to this space, and happy to share more today.
Thank you so much. And rounding out our panelists this morning is Millie Chapman, incoming assistant professor at ETH Zurich and National Center for Ecological Analysis and Synthesis.
Hi, everyone. Thanks, Nate, for the great introduction, and also really excited to be here and for the conversation. As Nate mentioned, I'm an incoming assistant professor of environmental policy at ETH in Zurich and a postdoc at the National Center for Ecological Analysis and Synthesis in Santa Barbara. A lot of my work is thinking kind of more closely to what Bistra was just discussing about, like, how do we leverage all of the data that comes out of these AI algorithms, and how do we integrate them into decision-making processes? So a lot of that is thinking about resource allocation problems. Where should we put protection and or restoration on a landscape, and what might be the implications of that on biodiversity? And how can computational tools help us assess those different implementations of policies and come up with strategies for effective policy design. Other parts of my work are really concerning kind of the ethical implications of leveraging large-scale data for decision-making processes in the conservation domain. So as I think we'll discuss throughout today, a lot of the underlying data that goes into these AI algorithms is quite biased. And so what are the implications of that on our downstream decision-making processes, particularly as we start to increasingly rely on computational tools for those decisions in the first place? So yeah, excited to be here.
Yeah. Thank you all. I'm really looking forward to this conversation. To the rest of our audience, please use the Q&A feature to submit questions. They'll be reviewed and passed along to us by our able assistants from the California Council of Science and Technology, and we'll try to work them in as we have time. So starting off with a first question. We've already dabbled in it a little bit, but for each of you on the panel, what are some of the notable examples of how AI technologies are being used for biodiversity conservation in California and in other states? And let's start with you, Sara.
Yeah, I think there's a couple really amazing examples, particularly in California, that I'd love to highlight. So the first one is the partnership between the California Department of Fish and Wildlife and Wildlife Insights, which is an online platform for storing, identifying with AI the species in, and analyzing, sort of doing additional inference ecological analysis on top of these sort of static monitoring cameras, camera traps, trail cameras, that are placed sort of all over the state to help manage our natural and our public lands. And so, for example, Wildlife Insights, this partnership with Wildlife Insights, which is a much larger consortium of about 30 NGOs, and the AI is supported through Google. It's enabled them to both increase the security of the photos, but also, I think, much more importantly, to holistically manage all of that data across the different partners who are collecting the data in different regions of California. And this allows information to be very easily shared. And then you're also able to do assessments of wildlife and communities at landscape scale. So, across these different individually managed monitoring sites. And to date, I think there's been about 32 million images from over 10,000 camera traps that have all been collected in the state of California that have been uploaded to part of that Wildlife Insights platform. And one of the kind of exciting, how that transitions back, from both the data, also the development of AI, and then how that goes back to the open source community. Just yesterday, Google and the AI team at Wildlife Insights, which I've been a part of for about 6 years now, we just released an open source version of a global camera trap species identification model that's reasonably accurate for over 2,000 species around the world. And I'm really excited to see how, that type of community-driven collection of data sets that enables the training of useful tools using AI to process data can then sort of expand the usability and kind of iteratively improve those models over time. And then maybe in a bit less detail, 2 other really exciting examples. One of them is the detection of individual trees in urban forests using aerial data across the state of California. This is being led by Jonathan Ventura at Cal Poly SLO. And then also additionally at Google, we've looked at actually using Google Street View imagery to be able to identify the species of all of those individual trees, which allows cities to actually actively plan, understand the health of their urban forest, understand risk factors for things like particular pests, and potentially more actively manage maybe the equity of access to green space over time, which is really an exciting opportunity. And historically, this just really wasn't possible at scale because doing a manual tree census can be millions of dollars per city, depending on the number of trees. So it really decreases the cost for that type of sort of active management. And the third example is monitoring fisheries, particularly salmon fisheries across rivers in California and actually all the way up to the state of Alaska using in-river passive sonar cameras. And so in these cameras, this because you can't sort of see through the water at all times of day, you're actually collecting sound imagery that lets you detect and track the individual fish swimming upstream and downstream. This gives you the ability to estimate what's called escapement, so the number of fish that are actually sort of actively making it upstream to spawn, which gives you a sense of the sustainability of a fishery and lets you make active management decisions around fishing quotas. And we're currently using AI to actually try to do that detection and tracking and counting in a semi-automated way with experts in the loop. And this really reduces the kind of human cost of monitoring and managing all of these different rivers. And one example of an explicit sort of active partnership and deployment is with Cal Trout, where we're working to actually monitor the resurgence of a salmon population after the Klamath Dam removal. I think these are three pretty diverse versions of the use of AI for processing and sort of improving humans' ability to scale to data that are all different data modalities and kind of different types of use cases. And I think it really illustrates the breadth of opportunity for AI in these spaces.
Thank you. Same question to you, Kumar.
All right. Let me bring one example from the East Coast. So Chesapeake Conservancy worked on a wetland AI model a couple of years ago. So wetlands are extremely important for a number of reasons. I'm not going to talk about it. However, the question is, there is national wetland inventory data. And that data is compiled by people visiting the field and mapping the boundary of the wetland. And the problem with that approach is it's super expensive. And the problem is wetlands are kind of, they change the position every season. And sometimes they appear, sometimes they disappear, sometimes they are not even seen from the space, and then so on. Now, what can we do to get an accurate map of the wetland? Because conservation of the wetland begins with accurate mapping. And since these are moving target, we need a system that maps the wetland almost in like a real time, let's say on a seasonal basis. So a colleague of mine, Mike Evans, and I worked on wetland AI model, and we also collaborated on this AI architecture with some other agencies. And the goal here is to create an AI system that grabs the completely freely available satellite data on the fly with zero data processing and zero feature engineering. It predicts the wetland. And it does that at a very high resolution of 1 by 1 square meter. So the algorithm tells if there is a wetland in every square meter. With that, we get a very detailed boundary of the wetland. And you need a new updated map of the wetland next season, grab the satellite data again, and then make the prediction again. And that gives us the updated map. So a couple advances in terms of methodology is we are able to achieve very high accuracy of 94% using completely freely available data. So no proprietary data were used. And another is this helps in democratization of the data because suddenly the tool is available to others to use and make predictions in the area of their interest. So now one caveat here is the model is still, we are developing the model. We have tested it in many regions. It works very good, but to make it available for the entire continental US, we need more training data. And my colleague, Mike Evans, is working in making the model more generalizable. Thank you.
Thank you. Bistra, do you have anything you'd like to add in?
I guess one of the most obvious ways, I think most pervasive ways AI is already being used in addition for biomonitoring, which, both Sara and Kumar gave examples of, is really in species distribution modeling, right? So basically understanding where are the suitable habitat for specific species. So that is really a prediction problem where you want to correlate environmental information like elevation, precipitation, land cover, and so on, to whether specific location with those characteristics will be suitable for species X. And so we train this model using actually machine learning approaches based on observations of where these species have been spotted in order to elucidate this relationship. And for example, occurrences, spotting of animals is very much relying right now on camera traps and other sensors deployed in the field. But these models basically use this historical record of occurrences, learn these relationships, and then are able to predict what is the suitable habitat. And in addition, because they ingest things like precipitation and temperature and other environmental factors, we're also able to use them to project into the future by using climate projections of how these things might change over time. So that's, I guess, one of the most prevalent examples of using AI already in many different studies and agencies and policymaking.
Thank you. Millie, you got anything to add for us? I know you do.
It's hard to be the last to go. No, I mean, I think that really covered like the scope of kind of the current applications of a lot of these methodologies in the biodiversity space. And I think Bistra's last point about species distribution models and kind of scaling up the information that we do have, because for every species, we can't necessarily do a full-scale census of the state of California, and even on larger scales, that is further difficult. And so having the methodologies to kind of fill in the areas that we don't have information, I think is, and predict where species are, or where wetlands might be, are really cool applications of some of these methods.
Thank you. So we've heard a little bit now about sort of the tools that are currently in use, and even admitting that that's only a thin layer of what's in use. But I'm curious about I'm more curious about the future. What do you see as being some of our greatest opportunities for new avenues in the management and conservation that result from bringing AI into biodiversity conservation practices, whether it's planning or active management. I'm going to toss this one first to Bistra.
Thanks, Nate. Yeah, so I think one of the underutilized areas is more in between this kind of immediate, like processing sensor data immediate, and in between the very long-term planning for climate change and so on, is really more in the short term and medium term. How can we use AI to be able to more dynamically respond to changes, right? Like adjust policies or management decisions on the fly. And I think that's where I see a very exciting opportunity for more help from AI to support effective decision making. For example, there's still a lot to do, but we've quite advanced actually the use of AI in disaster response and recovery for humans, right? After a wildfire, after a hurricane, we have quite a bit of AI tools that are very actively used to detect, where buildings were destroyed or where to deploy resources to help humans and recover. I don't see the same a use and incorporation of AI to think about the same in the context of habitats, right? After disaster, how can we leverage AI to understand what's happening? How can that maybe change our priorities and how to incorporate that information as quickly as possible to respond to protect or restore critical habitats in the wake of a disaster. So that's, to me, one kind of unresolved and underutilized areas. There's many others, but I'll let others speak to this question as well, because it's really open-ended.
Okay, thank you. Passing along, Kumar.
Sure, yeah. So I want to bring two ideas here as the user of AI in conservation and biodiversity. So one is along the lines of Bistra, what's talking about. Let's say real-time monitoring, right? To me, working on a number of conservation problems, what I have found is we have the architecture, we have the computational capabilities. But what it's lacking at the moment is a very precise data that has been collected routinely at a very short time interval. And to make predictions in real time, we need those kind of data sets. Historically, that has never happened because the type of models that we use in the past aggregated data for 30 years to make predictions for biodiversity. And now we're talking about seasonal data set. And when that data set is available at very high resolution and also at very high dimension, meaning that has to capture different aspects of the nature and the environment and the surface and hydrology and climatic conditions and all the other aspects of the system. And only with that, the algorithm will have power to make predictions in real time at a very precise location. And I think that's coming. And since we are getting a lot of a new type of satellite data set, our capacity to do more of the real-time predictions is getting better. Second is precision conservation, which is what my organization does a lot. And precision conservation meaning we want to exactly know what's happening at very precise location rather than making a prediction of, let's say, species distribution at like kilometer by kilometer scale. So 1 by 1 kilometer is probably one of the finest resolution for biodiversity mapping in the traditional STM framework. But if you are modeling a frog stays in a very specific kind of microhabitat that is present only in certain location within that 1 by 1 square kilometer area. So precision conservation is another aspect that I'm looking at, because as we have more and more precisely collected data set, that helps us with precision conservation, and that can help us for a number of problems, including allocating our resources only in the proper area for conservation. Thanks.
Thank you, Kumar. Millie, do you have any insights you'd like to share?
Yeah, I think just building off of Kumar's last point about precision conservation and Bistra's earlier point about like making decisions when we are resource constrained, whether that's like resources in terms of like dollar amounts invested in conservation, but also like other demands on land for production, for like whatever it is that we use land for. I think AI like provides the capacity to potentially come up with strategies for implementing conservation or restoration interventions in really spatially refined areas that are super critical, but also like temporally refined. So if we're talking about wetlands that are seasonally flooding, can we better understand like what times of year it's most critical to be reducing pressures on those areas or flooding those wetlands so that migratory species can utilize those habitats along their pathways. And so, yeah, I'm really excited about kind of some of these applications to kind of decision strategy, kind of moving past simply the prediction issue. And I think just going back to one other point from Kumar about kind of all of this data being aggregated and these kind of real-time both data streams and like near real-time predictions. Sometimes actually that becomes like too much information for us to effectively process as just humans. So can we come up with systems that help us kind of synthesize all of that data into actually the critical components of the decision that we're trying to make? So like what information do we actually need from all of that kind of spatially resolved data that can help inform an effective decision?
Thank you, Sarah. I've been seeing you nodding along. It sounds like you're in agreement. Got anything more you'd like to bring in?
Yeah, I completely agree with all of these points. And then I think the last thing that I did want to highlight is that it would be a bit naive of us to be talking about AI currently without thinking about how human language and the sort of explosion of large language models and vision language models might be influencing or changing the opportunities for AI as we move forward. I think, of course, all of those come with a lot of challenges, both in terms of the climate cost of training some of those very large models, but also in terms of the kind of risks of using them. I'm sure many of you have heard terms like hallucination, where these models can sometimes make reasonable sounding, but actually factually incorrect types of errors. But I actually think there's a lot of opportunity for introducing this type of language supervision or this like ability to interact with data using human language for policymakers. And one recent project from my lab that I think has been kind of a cool way to think about how the intersection of language and data can sort of expand capacity is thinking about enabling users to actually search the entire set of iNaturalist images, so 290 million global iNaturalist images using text, based on the efficiency of sort of large-scale vision language models. And so then you can think about letting any expert via only sort of text prompts potentially surface anomalies, new information. All of that data has been labeled with just a species label, but captured in those pixels are examples of behavior, morphology, human-wildlife interaction, sort of fine-grained examples of weather, response after fire. There's so much information in the data we've collected that we just can't currently harness. And I do think that these kind of foundation models in some ways are opening up new avenues of discovery and interaction for even non-AI experts on already collected data sets.
So many interesting possibilities. Moving along now and changing tactic a little bit. We've discussed some of the underpinning opportunities, both the ones that are currently in use and the ones that are maybe still in front of us. But translating this into action on the ground is going to be important. So how do you think policymakers should approach using these tools to inform management decisions? What are some of the potential challenges in translating the output from the tools into actions on the ground and making decisions relevant to conserving biodiversity? I'm going to start out with you, Millie, on this one.
Great. Great question. Very hard question, I think, and something that I think the broader community is grappling with a lot. I think my first point to this is that ultimately, like a lot of decisions that policymakers are trying to make and or land managers or most people in the like conservation domain are really like value-driven decisions. And so at its core, like AI and the data that comes out of AI is critical for informing those decisions, for allowing us to effectively meet our objectives. But like it ultimately rests on like the community kind of agreeing on what the goal is. Like AI is not going to decide that for us. And so I think that sometimes it's it can become a challenge of making sure that we're not like just pointing to AI as a solution to a problem that we haven't actually decided on as a community. And yeah, I guess other things that I think that I've been thinking about a lot in this space is like, how can we better collaborate from like really early on in the process of developing these tools with actual decision makers or policymakers to ensure that actually those values are well reflected in the outcomes of the models or the outputs of the models, such that they can actually use the outputs in their decision-making processes. So again, like what sort of information do they actually feel is lacking from that decision-making process in the first place? So can we, as a society of environmental scientists, of computer scientists, actually work more closely with policymakers and decision makers from the get-go?
Thank you, Millie. Kumar, do you have any thoughts on this one?
Sure. I think it's kind of a little vague question, but I want to bring the idea of, let's say, transparency and collaboration. So these AI models, these AI algorithms, they learn the pattern from the data. That's the source of their information. So that means depending on the quality and the quantity of the data, when I say quantity, the data has to represent comprehensively the truth, the underlying truth of the system. And if you don't have good quality data with good quantity, then the AI is not going to learn the actual pattern of the system that you are modeling. And in that situation, you can still tell the world that, hey, I have 99% accuracy, because the accuracy is measured on the data that you have in your hand. And that accuracy sometimes can be completely useless metric. That's why we need a number of steps in the entire process. And the AI has to have very high transparency and interpretability. Well, interpretability is a big challenge in AI system. That's the innate nature of the algorithm. But the policymakers should do their best to understand how it is performing, so that it is to the interest of the public. And the next I want to emphasize here is, I have worked with so many experts. They're really great experts in their domain, for example, species or system, and they doubt the statistical or machine learning models. The same way, the machine learning community may sometimes dismiss the expertise, but the solution needs both of them. As Millie and Bistra was emphasizing this, we need a comprehensive approach where we bring the powerful technology of AI and machine learning, but at the same time, we need expert opinion to kind of, understand it, validate it, think about it, revise the model, and use it. Thanks.
Thank you. This has been really interesting, and I'm going to try to start leading us maybe a little bit into some of the challenges associated with the use of AI. So what do we have? What types of gaps do we have within this field? Policy, funding, data availability, staff that are appropriately trained. That are limiting our potential for deploying AI into conservation applications. Since you'd already started to lead into that a little bit, Kumar, do you have a little bit more that you'd like to give on this before we start moving on to our others?
Sure. I want to bring just one idea here, which is again data. So for me, the availability of the data is one thing that makes my AI model, powerful or useful. So we are getting more and more data at higher, temporal frequency. That's what we need for kind of real-time monitoring. And when I say real-time, I'm not talking about like daily or weekly forecast of something. Even if it is seasonal, then that's something like real-time for me. And that needs more data at high resolution. A practice that's in biodiversity mapping is people grab the freely available data set and to create the final resolution data set, they downsample it. And when they downsample it, you are not creating like data, you are not creating information, you are not, all you're doing is you're downsampling the coarser resolution data that may not match with the reality. In fact, it does not. And that's not a best practice. And in the absence of the actual data collected at the native resolution project, that's what we do. But to really understand, to really make it more useful, we need finer resolution data. So I think, to me, for biodiversity, we need better data, high dimensional data, higher resolution data collected at higher temporal frequency. And I think with that, we'll be able to train very powerful models for biodiversity and conservation. Thank you.
Thank you. I know that Millie, you're deep into the data side of things as well. I'm curious to hear what you think of these challenges.
Yeah, I mean, I think it really is like at least one crux of the challenge is like having the appropriate data to actually like derive insights about ecosystems and the ways in which they're changing, to inform like effective and equitable strategies that aren't like propagating the biases in our underlying data. I think just going off of Kumar's point, like at some level, like we could collect data and feel like we need more data always. And so I think that there's also a challenge of like, where do we need data and what do we need data on? Like, where are the most critical data gaps? And like, what is the actual value of the information that we can derive from a given place or a given taxa in a given place? And so I think actually this is another place where there's a lot of discussion in the community about like, how do you design kind of monitoring strategies that can like really truly improve our modeling capacities, and how do we think about actually where those need to be improved for the most critical decisions in conservation. And this is another problem that I think comes back to this idea of collaboration across computer scientists, ecologists, and policymakers to really make happen in an effective way.
Okay. I'm really curious, as we continue this discussion, about some of the underlying infrastructure that's needed to inform these types of applications. And I know you've been tied into that, Sarah. Do you have any thoughts on those?
Yeah, actually, really directly building on Millie's point. I'm someone who works a lot with different types of stakeholders, different types of practitioners, from NGOs to governmental agencies to corporations who are thinking about trying to assess their own biodiversity impact. And one of the things that is true across the board is that resources for this type of work are limited. Like, we don't have infinite resources to collect what might hypothetically be this magical set of data that captures everything everywhere all at once at high resolution. And so I think Millie's point about data prioritization is actually also really closely tied to the fact that we need to be optimally allocating our resources. So we need better understanding of which data points are going to be adding the most value so that we can think about making the best of the money that we have. And then another point about that infrastructure, like, not only is the collection of the data not free, the storage, the management, the transmission, and the analysis of that data is also not free. And it actually requires a good amount of software engineering, of experience with sort of navigating different types of data centers, maybe the cloud, making complex decisions about, whether data should be local or sort of accessible everywhere. I think one of the biggest challenges that I've seen to the scalable adoption of AI across all of these different types of stakeholders has been a lack of readiness in terms of their data infrastructure. So they're actually systematized, standardized, kind of interoperable sets of data. And unfortunately, this is the type of thing that can often be very difficult to sustainably fund. it's not necessarily something that's kind of sexy and new and the most modern AI. It's actually just brass tacks. Like, how do you build systems that are stable, that are maintainable? And we can do this with the limited resources we have. And also, how do we kind of navigate some of the both like infrastructural, but also political disagreements across different agencies or different organizations so that we can kind of agree on similar sets of standards and think about ways to share information. So I think that infrastructure ends up being a pretty key bottleneck for many people. And one of the biggest dimensions of being able to scale that infrastructure is actually just having people in those agencies who have the knowledge, the skills, the capacity to both build more kind of data science ready systems and also potentially apply machine learning to their own data. So I've been thinking a lot about what kinds of knowledge or intuition or literacy we need to build at different levels of these institutional systems to try to be kind of ready to adapt to the new sort of world of AI integration. And even at the very highest levels, I'm not expecting, a CEO of an NGO to write code. But I do think that there's a lot of hype out there. There's a lot of people kind of selling things that maybe, like Kumar mentioned, are potentially sound a little too good to be true because they are. They're AI models that don't actually perform as robustly in the real world as they're claiming, whether that's, unintentional or not, just based on the ways that they're evaluating the models. And so I've been thinking a lot about building AI intuition in people like in groups like policymakers, like sort of decision makers. How do you understand what types of things you should be skeptical of? How do you understand what AI is good at and what it's bad at to understand like what types of problems pass the sniff test? How do you kind of cut through the hype and kind of all the different things that are maybe being sold to you by Silicon Valley and understand what's kind of ready for translation and is actually going to lead to tangible impact on the ground and like changes in decisions as opposed to potentially just yet another dashboard that doesn't actually influence something on the ground. So
Let me
I think
let
there's
me
a
hop
lot
in
of
here,
need.
Sarah, real quick. We've got some great questions queued up from our audience. Before I make that leap over, that I want to make sure I'm not leaving you out. Bistra, did you have anything you wanted to add to the sort of the challenges dialogue that we've just been having?
Just very short, like more on the other end, I think I agree with the point that building infrastructure and capacity on the data collection and using the data is good, is definitely needed. But I feel that things are even more dire on the really end, at the end of that pipeline. How do we get the policymakers and kind of decision makers to actually incorporate the outputs of the final models? Like, for example, the species distribution models build on top of those occurrences that are detected in the camera traps, or the fish population outputs from a model that's based on the sensors in the rivers and so on. And I think that's where we still have huge gaps. A lot of the knowledge that AI generates still stays within the academic community or within high resource organizations, like, for example, the Chesapeake Conservancy, which has data scientists on the roster like Kumar, versus a lot of other organizations or agencies that don't have that capacity. So I feel that that's a big gap that we need to address, is how to improve that, facilitate that adoptions. How do we need to package the outputs of the AI to act as decision support for those decision makers and policy makers, and how do you even let them know what's out there, right? Because I feel like a lot of the things that are already out there are not even integrated. So that to me is one of the biggest gaps. I don't have solutions, but it's a it's a thing we need to plug.
Okay, so on to the first of our audience questions. And I'm going to sort of leave the floor open with this one, kind of see who has a first immediate response for it. And this is about the questions of some of the questions about the dangers of AI based conservation tools, particularly ones that oversimplify or start to take a more homogeneous approach to these complex and heterogeneous nature the complex mixed relationships between phenomena in these landscapes. How do we manage and mitigate those risks? And I'm going to ask us to try to keep this relatively quick so we can get one or two more questions in. Who wants to go first? I know you're not all shy. Millie.
Yeah, I mean, at risk of like not knowing the answer is the answer, right? That's like a hard question, but that's also a question that like exists in our current approaches to coming up with management strategies, that we're always risking like oversimplifying an indefinitely complex ecological system and therefore having like a misguided decision. And so I think, yeah, it's balancing like when and where these tools and the data that comes out of them or the insights that come out of AI methods, where it can actually help reduce those sort of simplifications that currently exist in our decision-making processes. So where are we already having to kind of overlook a lot of complexities in ecological systems, and where do we wish that we actually didn't have to do that? And that's, again, a cop-out answer because I don't think it fully addresses what the audience was asking.
Anyone else want to respond? If not, I have a couple others that are questions that are, I think, pretty interesting. So one, and I know that here in California, we've had very active traditional taxonomic collections and monitoring data associated with these. How do you see those? What is their role and importance to ongoing applications in biodiversity conservation of AI? Sarah, I think you might be primed for this one.
Yeah, perhaps. I mean, I think there's a lot of different ways you could go with this question. So one of the things that that I think is interesting when you're thinking about taxonomy is how fungible it is. So like, you know, there's kind of this idea, I think, for many people, actually also for myself, I didn't come up, I was trained as a computer scientist, not as an ecologist formally. And I was so shocked when I realized that kind of these classical definitions of taxonomies that I thought were kind of very rigid were actually quite flexible, changing all the time and in active disagreement across different communities working on different species and across different countries. One of the things that I think is kind of cool is as we're sort of trying to figure out how to train machine learning models now from what is potentially not a unified taxonomy, you can think about trying to understand whether or not it matches with the true underlying taxonomy of species, reasonable clusterings across those taxonomies that might actually help us with one of these really standard problems in biodiversity monitoring, which is mapping between different disagreeing taxonomies from different organizations. So I think there's some really cool work actually at University of Arizona trying to think about universal, basically translations between these sort of hierarchical trees of taxa. And then on the other side, one of the things I think is amazing about stuff like iNaturalist, which kind of pairs the power of like letting community members or citizens engage directly with science with something like AI, is its ability to teach non-experts to become taxonomics experts through interaction both with AI systems, but also with existing communities of experts. And one of the things we've seen is that via iNaturalist, you know, maybe these people were already out there, but some of the best experts on identification and kind of coming up with these kind of characteristic or dichotomous keys for species, this understanding of what makes a species that species, what traits are most important. Those experts are someone's grandma who lives, you know, in like some rural part of California who just loves spiders and like has learned much more about spiders than sort of many of the other experts in the area. And I feel like this kind of democratization of the scientific process and of thinking about what it means to kind of interact with science and build expertise is quite cool. So I do think that some of these AI systems have enabled more people to become taxonomists and then to think about being those data collectors of that high quality, fine-grained observation data, sort of at much broader scales.
Okay. I don't want to cut anybody off. I would love to continue the conversation. One more, hopefully quick question from the audience. As we all know, AI and data centers, particularly in the training phase of models, can be enormous energy consumers. So we have a question about how you reconcile the potential impacts of that energy consumption against the very values that we're trying to protect. Do we have anybody that wants to jump out in front of this one first? Kumar, I see you've unmuted.
Sure, yeah. So it's a good question and something that we should think about before embarking on a model. However, a good thing about AI systems is you train a model, and then when you have new data, you don't have to start from the scratch like any other kind of statistical or traditional machine learning models do. You keep improving it. You keep building on the previously built model. So even though there is an initial, cost carbon footprint of the model, it's not like that always. And another cool thing about AI models are they are by nature generalizable. Okay, what that means is you use random forest to make wetland mapping model. Then depending on where you are working, you have to retrain the model again and again and again and again, because these models are not normally especially transferable because they are not generalizable. On the contrary, computer vision based models like the ones that we have been training and working on, they have very high generalizability. So that means once a model is available there, then we don't have to retrain the model again and again, like in the traditional sense. Mm-hmm. So I believe it's a trade-off, but in the longer run, it's actually helpful.
Anybody else want to chime in the last few seconds we have before I need to turn things back over?
Sure. I mean, when you think about the computational costs of AI, I do think that one thing that kind of gets lost in the nuance of these conversations is that not all AI is created equal when it comes to computational cost, both of training and at inference time when you're actually running that model on data. Most of the AI we've been talking about today, with the exception of those large language models I talked about, it's small AI. Even if these models are big, they are relatively much more small. And we actually design them to be small so that they're resource effective, so that we can run them on the edge on low cost computational infrastructure. The relative cost of most of the AI that's happening in AI for conservation and is actually being deployed is really a drop in the bucket versus the climate and computational costs of, the OpenAI models, the Google models, the IBM models, the Microsoft models of today. And so I think it's maybe another version of that kind of common thread of to solve climate change, you all should really focus on your own personal use versus potentially thinking about the relative costs of kind of large scale corporate use. So these really are not in the same conversation at all.
Thank you. And thank you for that clarification.
100%.
With that, I think I'm about to get the shepherd's crook. So I think I need to be passing the baton back to Jason to help us with any final words.
No, thank you so much, Nate. Thank you for joining us today and moderating, and thank you so much to our incredible panelists for taking the time to share your expertise and your guidance, for answering these questions, for thinking through such a topic that has so many different nuances to it. We really appreciate you sharing your time. And thank you to everyone who joined us today. If you'd like to watch this briefing again, or if you have a colleague who is interested but couldn't make it today, it will be posted on our website, and we'll be sending out the link with follow-up emails. And please also keep an eye out for additional briefings throughout the year as we continue to dive into some of the many facets of this topic. Thank you all so much again for joining us today, and we hope you all have a wonderful rest of the week. Thank you.